Hello, everybody. Peter, like Emmerick mentioned, or at least I was part of the Innoptus Solar Team last year as an aerodynamics engineer. And as an aerodynamics engineer, of course, we used a lot of CFD simulations to design our car, optimize our car, and to compete in the World Championship. For the people who don't know, the Innoptus Solar Team, it's a student team from the University of Leuven, where we build a solar car in a time span of one single year with 20 students in total. So you can see the team of last year, of which I was part. And of course, to build a solar car, you don't do it by yourself. You need a lot of knowledge of what you're building. You need a lot of simulations, a lot of data, so you know what the car will be doing. We have been doing this for quite some time. Last year wasn't our first year. In total, we have built 11 solar cars already. These are the 10 previous ones, and then the one from last year is the final one that we have built. So already over 20 years of experience, and over the years, you learn how to optimize your workflow, your way of designing such a car, all the stuff that comes into play when making such a unique thing. And with this experience, we really are part of the best teams around the world. We competed in all kinds of countries. Myself, I raced in Australia last summer in the World Championships, but we already raced in quite some countries, Belgium as well. We are going to America this summer for the first time. And over the years, we have already won some pretty significant prizes. We became world champion twice and already European champion 3 times. So we really got the way of working right in terms of designing this car and really knowing how the real thing corresponds to what we have been designing. But of course, before being able to race this thing in Australia, you need a lot of knowledge on this car, a lot of data. For me personally, as an aerodynamics engineer, it was a lot of CFD. So we knew how much power we were going to consume at different speed regimes and which design parameters had the biggest influence on this power consumption. And this brings us to the CFD workflow that we implement at the Solar Team. It's actually pretty basic. It's a pretty standard one. We start from our CAD model, go into some geometry preparation to further advance to the mesh generation in Ansys Fluent, and finally hop onto the VSC infrastructure to get some rapid simulations. And with these outputs, we go back to our CAD model to improve it, to optimize the aerodynamic performance. For the CAD model, we were using Creo Parametric, which was very useful since we could create a completely parameterized solar car design in which we could adjust all kinds of parameters to run some sensitivity analysis on the aerodynamic performance to see which curves have the biggest influence on the drag, on the overall performance. So a lot of tweakability in your design and a very fast way of producing hundreds of design iterations. But of course, these iterations need to be simulated in CFD. And this brings us to our geometry preparation before running the CFD, which we are doing in Ansys Discovery. It's a very useful tool since we're able to completely automate the workflow through a very user-friendly script. And also we can create named selections of the nose of the car, the tail of the car, you name it, and you can make a specific selection of that part of your car to analyze in detail in the post-processing of your CFD simulation what is going on there, what forces are generated, what moments are generated, which is like everything we could have asked for. Once the geometry is prepared, we go over to Ansys Fluent, where we start with our mesh. And here as well, the workflow is completely automated. You can create your optimal meshing settings and make an automatic script that just runs your geometry through all these meshing steps such that you end up with a final mesh with good quality and with very little effort due to the scripts that's ready for the CFD simulation. Once you have this, mesh, you're ready to go and solve the geometry, go to the CFD solution. And since we really are looking at aerodynamic values that are in a very, very low range, we really optimize for lowest drag. We need very good accuracy. And with accuracy comes very high mesh resolution, leading to very heavy simulations that we need to run that aren't very viable on standard desktops, even the more beefy ones. If you're looking at designing something and doing rapid design iterations, and that's why we work together with the VSC, the Flemish supercomputer, where we can just insert our Fluent case or our mesh with the solver settings. We can script everything that we need to change, for example, the velocity, the angle of which the wind is acting on our car. And with all this data that we provide to the VSC, we can just use the Slurm scheduler to submit our jobs, our Ansys Fluent simulations. It's pretty similar to what Emmerick talked about. And then that's it. We just wait, depending on what kind of simulation we are running. We get the results, and then we can start this loop all over again to try and improve the design, and in the end come to the best design possible. Throughout the project, there were a lot of different phases, a lot of different types of simulations that we needed to conduct to end up with the final product and to really gain that aerodynamic knowledge of the car that we have built. Of course, like every product, we start in a design phase. So we list all the requirements, all the regulations that we need to satisfy in order to be able to start the race we are competing in. And in a design phase, everything is still open. Everything is free, and you can really go ahead and look at, okay, which designs work while still satisfying all the requirements that were given to us by the organization. And in the beginning, it's really broad. You look at all kinds of designs, like you can see on the slides, existing designs like a trimaran, a catamaran, or a bullet design, which we went for over the last few years, but also trying some new stuff, because for every race, there are new rules, and new rules means that there are maybe new loopholes that you can exploit. So in this phase of the project, it's really important that you can iterate very quickly and get a quick glance of which designs are performing and which designs are not performing at all. In these kinds of simulations, it's just external aerodynamics of the body, no rotating wheels, just looking at the aerodynamic performance of the body. It's a steady state simulation, and with a high quality mesh with good resolution, we approach 10 million cells, which on the VSC infrastructure leads to a simulation time with CPUs of 30 to 45 minutes, which during the project we were very, very happy with, because we could just schedule all like up to 10, 20 cars in parallel. They were simulating, and in the meantime, we could design other cars. And when the simulations were done, we could start the new designs and so on and so forth. So it was really a very streamlined workflow. So for these simulations, it was really like constantly 24/7 running as much as possible. Once we got a good idea of which design worked best, in our case was the bullet shape, we went deeper into the details of the design and more into the curves, the fillets, the rounds, the tail, you name it, all the details we tried to study with different parameter sweeps, but also looking at the performance of the car when they are put under side wind conditions, especially in Australia, where we did our race. Crosswinds are very, very severe and can really affect the performance of your car, especially since you also aim to make it as light as possible. So you want to have a good idea of what will be going on aerodynamics-wise when you catch some kind of crosswind. These simulations, in terms of setup, are pretty similar to the previous ones, but here it was even more necessary to be able to run a lot of simulations in parallel because it's pretty easy to change a certain parameter in your design and get this CFD workflow going because everything was automated. So we were really looking at the fastest simulation times possible in order to avoid any kind of bottlenecks, and that we were still able to produce as many iterations as possible to simulate and to see which parameters were best in which cases. Besides designing the car and the complete body, we also focus on aerodynamic innovations, one of which is the fin on the car that we are using. It's been there for a couple of years already, and the main goal of the fin is, in case you catch a side wind in a certain scenario, that the forces generated by the fin generate a thrust that decreases the power consumption of your car, and it's overall better for the performance. So that's the main idea of why we put a fin behind the pilot, which is sticking out in a picture, to gain that thrust force in under side wind conditions and lower our power consumption. And the first wing or the fin designs were just a single fin, symmetric airfoil. It worked pretty well. We saw in our strategic data that the power consumption did indeed decrease. But in our year, so last year, we were looking at, okay, we have one single fin, it works. But what if we switch from a single fin to two fins with both a cambered profile instead of a symmetric profile? And that was a pretty difficult decision to make, to see, do we stick with the single one? Do we go to the double one? Which required a lot of simulations and a lot of crosswind simulations, which automatically become more heavy, bigger mesh sizes. And that was like the first step in getting this innovation going. Like, is it worth it to go to the double fin? And as you can see by the amount of cells, we went up to 50 million, sometimes even 20 million cells under severe crosswinds, which also increased our computation time. But also here, especially when you want to make the decision fast, you want these fast simulations. And in the end, after a lot of trial and error, a lot of experiments with different cambered airfoils, we came to the conclusion, all right, we are going for the double fin in our car, which can be seen here. It's in the picture, it still looks like a single one because they are very close together, but we went for two different fins. And that was a first step, because the second step, once we made this decision, is all right, we have two fins, but which airfoil is the most important or the best one in our application? And once again, this required a lot of iterations, a lot of simulations to see which design parameters of the fin itself, so height, width, you name it, affect the aerodynamic performance, combined with which airfoil is the best. And as most of you probably know, there exist a million of airfoils, and to choose or to find the best one requires a lot of testing, which required a lot of parallel simulations to find the best airfoil. Besides the fin, which is a pretty, it really catches the attention of the people watching or following the race, we also have other innovations like wheel covers, which is like put less into the spotlight, but also very important. The wheel covers are really important to us because the rotating wheels, they can bring rocks from the road, for example, in our car. They also bring rotating air inside the car. So you want to close the hole to the outside world as good as possible, which is done through wheel covers. And we aim to create some kind of housing around our rotating wheels that prevent any slippage of the wheel against the wheel cover, but also reduces like all the dirty air and mess from the road coming into our car. And this opens a completely different type of simulation compared to the previous ones we did. The previous ones were just steady state, the body of the car, looking at the performance, but here we're looking at transient simulations, rotating wheels, combined with the very, very tight gaps between the wheel covers and our rotating wheels themselves. So something completely new, also leading to completely different mesh, As you can see in the element size, we went from 10 million all the way up to 45 million, which is a very big increase. And we also felt that pretty hard in terms of the computation time. The combination of the transient simulation with a lot more cells led to simulations of up to 3 to 4 hours, meaning that in terms of design iterations and exploration, we were way more limited due to the fact that the simulations just took way longer and we didn't have the space or the bandwidth to conduct all kinds of iterations, meaning that we still got to a pretty decent solution, but if it's the best, we can't really say because we didn't have the computing power to do much more in the timeline we had. Besides these design simulations and the innovation simulations, we also want to see, all right, we do these simulations, they are pretty quick, but how well do they correspond to the reality? And that's what we did throughout our testing phase, which brings us to real life scenarios where we are driving on the Australian road or in Belgium, driving for kilometers and kilometers to see and monitor our real life power consumption and put that next to the CFD results and the aerodynamic drag that we were calculating to see, is this the case in this specific scenario? Do the real life results correspond to what we see in the CFD? And these simulations are like complete body simulations, so rotating wheels, full body, very big domain, which is pretty close to the wheel cover simulations that I mentioned earlier, also with a computation time of 3 to 4 hours. So you can imagine to get a complete picture of your solar car behavior in real life, you will have to choose your design points very carefully and look for a way to interpolate between different design points, since running every single scenario, every single speed, every single wind angle, it's just not doable with the time we had and with the computing power we had. But we still had to do it. The results were really nice, but of course, in the end, we had to interpolate between different scenarios to get the complete picture. Besides the performance of the car, we also wanted to validate the new innovation, the double fin, for which we went to the wind tunnel. And here as well, we wanted the complete wind tunnel setup as a simulation environment to see, okay, if we do the CFD of this simulation and compare it to what we get as a result from the wind tunnel, how well do they correspond? Is this what we expected, or do we need to change anything in our design to get the results that we need? So looking at the entire project, we had design simulations, we had innovation simulations focusing on smaller parts, but also like full picture, transient, big simulations, all with the same workflow on the VSC with the CPUs that we had available. We did a lot of simulations, over 2,000 over the entire project, which is massive, but it also costs a lot of time when putting all of that together. And up next, Emmerick will discuss the difference between the CPU time that we needed for all these simulations compared to the GPU time. There you can see like massive increases or massive speedups, which would have helped last year immensely in the design phase, in the innovation phase, in the strategic phase, and it's definitely something that we will be using in the future for the upcoming teams. And now I'm going to go back to Emmerick, who is going to discuss the results and the benchmarks of all the simulations I just discussed. Thank you very much.
Okay, thanks, Pieter. Okay. So let's go to the last part of our presentation. So what Pieter just walked you through are the real engineering challenges Innoptus team encountered, solving the optimization, innovating with the fin, and mapping the race strategy. 3 different CFD problems that I also want to further explore on the VSC. So let me quickly anchor the 3 cases. We start with the shape optimization. That's case one. That was the design phase of the team. Then we have the fin study, which is more the innovation phase. And then at the end, the race strategy simulation, the strategic phase. It's very important to mention that this complete overview from concept to race is just less than 1 year. They have to go to all these steps. So they have to find a concept, optimize it, produce it, also try to innovate to keep winning races or try to win the races, and then also the strategic phases. So time limits are very important and really influencing and impacting the complete workflow of the team. So these 3 cases I received from Pieter and the team were run on the CPU solver, and I used these specific cases and transferred them to the GPU solver. These are 3 aerodynamic simulations, so already supported for several years on the GPU solver, so I could just import the case on the GPU solver and start my benchmarking approach, which is similar to the one of the driver case. First of all, before we look at speedups, of course, also here we can check the accuracy and validate them to check the accuracy and trustworthiness of the GPU solver. 2 main parameters the team looks at is the drag force, of course. This influences your total energy efficiency, and the lift, which influences the stability of the car. In all these cases, we saw all values matches quite good. Definitely the drag forces are very good matched. We have to say we speak with a highly streamlined car, which has a very low drag. So we're really speaking about less than 0.05 Newton differences between GPU and CPU. And also qualitatively, we can see the skin friction coefficients matching quite well between both cases. Then in terms of benchmarking, I performed the same approach on these cases. First of all, the optimization. They did 1,500 optimizations on this car to achieve to this shape. The case was 10 million cells, so a bit smaller than the driver case, and that's also what we see in terms of scaling, both on the GPU and the CPU. But we still see huge speed ups if we even go to 1 GPU or 4 or 8. We can achieve high speed ups. The best case GPU is 0.05 seconds, which is 22 times faster than their current setup. Their current setup they used in the past was 192 cores on 2 nodes. If they just keep with the CPU solver, they could achieve speedups of almost 3 times. But if they then go to the GPU option, they can go to 22 times faster, which really means 22 times more simulations in the same compute window, because that's fixed for them. In terms of linear scaling, like I said, the off-scaling is happening faster, so saturates faster, but still we see huge speedups achieved both on GPU per CPU nodes as compute units comparison. Also here we see speedups of 5 to 8 times. So we see for the 8 GPUs, even though it's off linear scaling, these small cases exhibits quite high speedups for the small case. So even though it's not linear scaling, it's increasingly faster than the CPU equivalents. Also in terms of HPC licenses or compute units, we see 7 times faster for the same number of licenses. So if that's a limiting factor for the team, then even for the same number of licenses, they can go 7 times faster. Since the team is an academic team, for them the cost is not really impacting. So it's more simulation time, but also energy consumption. In the left, we see the total time needed for a simulation. These optimization studies required 800 iterations per simulation, which took them more or less half an hour, 20 minutes per case, which resulted in they could do 1,500 simulations in 420 hours. If they now go to the GPU, they could perform the same number of simulations in just 18 hours. Or on the other hand, if they want to achieve more designs, they could go up to 33,000 simulations in the same time window. Of course, that's not really feasible yet, because they still have to design, mesh their simulations, but it's showcasing the potential of how they can further explore optimization, maybe optimizing for crosswinds during design, or even higher fidelity simulations from the beginning on. But the team, of course, they run on sunlight. Energy consumption and their carbon footprint is also very important. So therefore, we look at energy consumption of the total number of simulations they ran. 1,500 simulations took them almost 400 kilowatt hours with their current setup. If they keep the same number of simulations, they could reduce it to 50 kilowatt hours for the same number of iterations. Of course, we can go always to GPUs and achieve the speedups, but of course it's not a fair comparison because we have to compare apples with apples. So therefore, I also highlighted this one. That's 2 GPUs, A100, so that's 216 SMs. That's more or less the same number of compute units than they used. So for the same number of compute units, they still can increase their speedups 8.8 times. Then after the optimization, so the geometry is fixed, they try to innovate to be competitive during the race, and therefore they designed and innovated and invented the fin to improve their stability, but also use the truss as a sailing effect. But of course, it's an innovation phase, so it's in between the already existing phases of design, building, testing, and racing. So their time to perform this calculation is quite limited, and therefore these benchmarks can really enable more exploration on these cases. Also here we see the CPU scaling is limited to only 3 times speedups compared to their current setup. If we then go to the GPU, then can go up to 13.6 times faster with 8 GPUs. But if you make these numbers a bit more concrete, so their simulation took half an hour to an hour. They have to wait. If they go to the GPU, let's say 4 GPUs, they can get the same results in 3 minutes. Or if they still have the same time window, they can run more geometrical variations, up to 13 times more profiles or concepts they can test in the same window, or more angles. They can actually perform a complete angle sweep. Let's say now they can run 5 different crosswind angles. They can now go to 65 angles in the same window. In this way, they can really optimize both for crosswind stability as increase the thrust or sailing effect for the complete map of wind directions, because they're never 100% sure how the wind will behave in Australia. So exploring more possibilities is definitely worth mentioning it. Or they can just go for very quick iterations. So if they have a very new out-of-the-box design, they can just throw it inside the GPU solver and get their results in 2.5 minutes which can then, if it's a good idea, they can further explore it in a fast time period. Or they can explore more detailed simulations, run all their cases transient, or even go to scale resolving simulations for better accuracy capturing. Then the last case is the race strategy simulation. This can be done after production, but preferably done after testing in the wind tunnel, testing on the road. Then they can really match their CFD domain with their tests to then further optimize their simulation workflow, running for different wind angles, speeds, rotating wheels to get a very good idea about the power consumption in Australia for different situations. So this one is almost 50 million cells, like the drive-out case. Important to mention, this one was a coupled solver, so not a simple or segregated solver. But we really see that these cases, coupled cases, even more benefit more of these larger bandwidths, because now they are solved in a coupled manner, which needs more data output during the simulation. So the numbers here are very impactful. If we compare the best CPU case with the best GPU case, we can achieve speedups of 38 times in the same time period. Like Pieter already mentioned, it's most of the time a relatively small time window where they want to try to have as much as possible simulations done to really get a good idea about their power output and behavior in multiple situations. So if you then look at the number of simulations they can do with the GPU solver, if you look at the simulation per run, it's 2,000 iterations. On their current setup, it took 3 hours. We could reduce that one to 0.08 hours for this GPU solver. If we then look at a fixed time window, for example, 4 weeks, where we can simulate as much situations as possible, then we could run 140 cases on the CPU. We can now go to 5,200 cases, or on the more energy efficient setup of 4 GPUs, we can go up to 2,300 simulations, which is the most energy efficient situation. So we consume less energy, but we still get more than 60 times more simulation. Which means that instead of running some sparse data points for different wind speeds, angles, we can now make a complete aero map for all wind speeds, angles, fin configurations. So with fin, without fin, double fin, single fin, they can all run it for all the different setups. And of course, also including wheel rotation, or even look at some LES simulations to get even more detailed results. So to conclude my benchmarks on the VSC, by means of this GPU acceleration, we can transform the CFD workflow of the team. CFD simulations will not be the bottleneck anymore. They can run as much shape optimizations as possible and go up to almost 40 times more strategic simulations, which means they can run a complete aero map of situations. For most GPU setups, they achieve a more energy efficient system. For GPUs, most of the time, 8 to 9 times less energy consumption with an identical CPU setup. The CPU scaling was limited. Was a hard limit for the smaller cases, but even for the big cases, it was limited to 2,000 cores. So we see that we could achieve speedups of 3, sometimes 9 times with the CPUs, but the GPU equivalents were very big. This resulted in that we can now completely generate a virtual prototype before the race in Australia. So based on our measurement data and our CFD data, we can generate a complete aero map of aerodynamic output in Australia. We can run each combination of speed, wind, fin geometry, and wheel rotation before racing to get a better idea and to design an optimal strategy in Australia. So to conclude, some outlook for the next generation. So of course, the A100 is already available for years, but NVIDIA and AMD are working hard on new designs. So I performed some small tests on H100 on our Azure environment. And then we can see that for one single GPU, we can even achieve speedups of 25 to 50% compared to the A100. And as far as I know, the VSC will launch a new supercomputer in the future with a lot of H100. So these ones can really even further improve the simulation speedups of the team and also the users of Fluent. Then I would like to thank you. Pieter and I are happy to take any questions from you on this topic and to discuss this very interesting topic with you.